Oh, good afternoon, ladies and gentlemen. Let's start the afternoon session, and I have the pleasure to invite to introduce the permanent participant of this event, Alexander Shostak, with his talk Bipolar Lattices as Codemans for Fuzzy Extensions of L topology.
Thank you for introduction. I guess that this title says very little to listeners. It is. I try to formulate as precise as possible what I am going to say, but to explain the meaning of it, I'll go to next, next.
Below.
Below. Here is the contents, motivation as usually, then the framework of the study, preliminaries, this means, then the main part, and then some possible conclusions. To say the main idea of what we are trying to do, the problem is, the situation is well known that in CRISPR mathematics, usually a property is either is or not is. In particular, a topological property of openness is in every topological space either open or not open. In case of fuzzy structures, it is possible to evaluate the amount of some property degree in this object. Yes, so this is the main what we are doing here to evaluate the presence of degree in sets in a fuzzy topological space, and then in the result we extend the usual fuzzy topologies to bipolar L fuzzy topology. So this is the main what we are doing. Here, so the first object we're working here is L topology. Now, at the beginning, it was called L fuzzy topology. Now it is usually called L topology, where L is a lattice. And the definition is very clear. Topology in X is a set of open sets, and axioms are empty set and the whole set are open. Intersection of two open is open. Union of a family of open are open. Here must certainly be tau, not L. And for L topological spaces, mapping is continuous if the preimage of every open set in the second space is open in the first set. So definition is very, very easy, and it practically appeared 2 years after this fundamental work. I think it was the first attempt to use fuzzy sets in mathematical structures. Now something seems not very natural here in the definition, or not finished in some sense, not completed. Sets are open. Sets are fuzzy. Yes, sets are fuzzy. But structure is usual, ordinary. Structure is ordinary, just a subset. And this was the idea of mine, and independently of Thomas Kuber, completely independently, that we defined fuzzy topology now as a mapping. So the fuzzy topology will be also fuzzy with properties, the degree. So it is the degree. Empty set and whole set must be completely open. Intersection will be at least as open as the minimum of these two. and the openness degree of the union must be at least as open as the infimum of all these degrees. And here one moment I would like to emphasize. So here are sets fuzzy and topology fuzzy. And first our first idea was to take L here and L here, but it was later became clear that it is better to separate these structures, because one is for estimation of fuzzy sets and another is for evaluation of their property. And actually, the definition of all these is practically unchanged, but the examples we have now, at least such examples, that if we take M2, that it will be chunk topologies in the previous slide. If we take 2 here and here L, it will be a Hurley's approach. And in the long run, in this talk, it would be important for me to use different lattices, L for sets. And okay, this is such explanation. Now, what we are using? We are using, as many research now start with residuated lattice. Sometimes some call them quantiles or Selmanoids or residuated lattice. The definition I will not say because I think everybody understands what we are speaking. For example, a unit interval and with a t-norm. And besides, we need here complementation. So reversing involution, and it reverse order. And typical is 1 minus a in the unit interval. Or another very important is in case of Girard monoid. I'll return to this later. I hope that I'll have time to explain the role of exactly this situation in our structure. A GL monoid has no. The CL monoid doesn't have. No. Once again, so this structure is any residuated lattice, any CL monoid and so on. This is additional operation, which a priori is not related. Yes. At the beginning, later it will be related. So in some cases related. Now we consider two copies of lattice L, one positive L and another negative L. And we define the order in the negative part just by reversing the order in the positive. So in the negative part, B is less than B prime, if in the positive part, B is larger or equal B prime. And now here can be defined suprema infima, and so this is no problem. Further, we unite these two different lattices and as a product. So now we have two lattices, and they look like this: L plus, and here L minus. And order is such: if here is some element A, B, then this will be larger than this, and this will be smaller than this. So in the result, this is the top element of the lattice, and this is the bottom element of the lattice. So these combined lattices defined, and operations here are defined, and so this is now the basic structure which will be used throughout the construction. Yes, here is written what I already explained. Union and complementation can be, and so I think I am going another way already. Yes, here are so comments that will how we will use this lattice. So this part for positive evaluation, and this part for negative evaluation of, in our case, open degree of set. It's here comments what I already told. Now the second, so one concept lattice with properties, another concept we need measure of inclusion. The measure of inclusion here is defined. I think for most of listeners it is known. We are looking belongingness of X to A, belongingness to X to B, how much AX is belonged below BX. If less, then it will be 1. If larger, then it's some calculation. And then we take infimum for all X and define inclusion of A into B. This is different variation of it are well known, and as I found, the most old references are these two. Later, many people used it. And the properties of inclusion is very, very natural. If you rewrite this in case of union and intersection, it will be just what everyone would can expect from the properties of inclusion of real lines. Now, we up to now we didn't use C, and the work can be finished at this point, but our idea is to continue it. To some extent, it is already finished, the first part. And now, going to second part, we need complementation. It is not related with residuum. It is defined like this. Star operation, EST norm, complementation, and this is the idea A doesn't imply B. A doesn't imply B. And the properties of this also one can intuitively understand what it means. Now the value of non-belongingness, again, the formula is here. I don't have time to explain, but actually it is also intuitively clear how we can evaluate that A is not included in, to what extent A is not included into B. Here are formulas. Now, yes, when I told that the first part could be finished, no. It was only the framework was finished. Now, what we are doing? We return to Chang definition fuzzy of L topological space. So every A is either open or closed, but it is different from, yes, it is this, as different from topological case when if A is interval, let's say, is not, it is interval as mapping. If it is not open, then its interior is already distance between them is 1. Point 1 here and here doesn't belong. Different in case of fuzzy topology, when a set may be not open, but its interior can be very close. So we can measure the degree to which interior is contained in no, A is contained in interior. And with this, the first theorem shows that what we have defined fulfills the definition of L-fuzzy topology as we defined with Thomas Puberg. It was in one of the first slides. And nuclear, here is some work done. This relation is functorial, so continuity of this mapping implies the continuity of construct of what is it is it is not mine. I am not ready to comment. Now we defined the degree of non-openness. No, just no, you see the formula. A is not contained in its interior. It makes also evaluation, and also a theorem that here is also everything okay. It is a mapping, and now it is already L and L minus, already L minus topology. And now unite all these topologies, and every fuzzy set, and not only fuzzy, and get evaluation of two values in this lattice. Yes, in this lattice, saying how, to what extent A is open and to what extent is not open. So here work is being done, but since my time is going to end, I would now turn to the case when these opens and non-opens are very well connected. What can be expected? I must say, it's not necessary, but it is one can want. It is in case when this complementation is the whole structure is Girard-monoid, and Girard-monoid, it is those who know MV algebra, it is generalization of MV algebra, and the definition is A implies zero is A. So double negation, not A and not A, we get A. And in this case, formula relations become very natural, and in particular in case of Lukasiewicz algebra, so unit interval with Lukasiewicz T norm. Then this pair is it seems like this. So it is one can say that it's the most natural case. Now, concerning the plans for further work, very much work must be done to study the relations between the original L topology and its extension. Then it is only one example of degree of openness, but can be considered also other different properties. Categorical properties, because we have now a category of L topological spaces and bipolar fuzzy topological spaces, categorical relation between them to develop to L uniform. And of course, some other questions can be asked, but it is always time going, and so thank you.
Thank you for your contribution. We can afford one short question if there is any. Irina.
The notion of continuous of a function. No, I think that I answered these, I told these, but not What here's the definition: the degree of preimage, not less. This is yes, it is mine and Quebec. Yes.
Can you characterize somehow
The same, but only we have now two. If the positive, now the definition of
No, I don't know.
no, but from definition it immediately we have two lattices. This mapping is again a mapping. So function is continuous if and only if the preimage is larger than the image. So to what extent to what extent the openness is, of a set, is a point in this square. So if it is here, it is completely open. If for non-openness we get 0, but for openness we get 1, then it would be completely open. If vice versa, it would become completely non-open.
I'm sorry, but I probably have to postpone your discussion. It was not a short question or short answer. So
no, the
okay.
answer is that this formula gives the complete answer. Only we can discuss what does it mean.
Thank you. Thank you once more. And it's time to introduce another traditional participant of this event. Oh, there's a post. Ivana Steiner Papuga, but it will be presented by Alexander Takachi, who probably was not here at the beginning of this series of conferences.
2008, so the third time.
Present a note on fuzzy measures in statistical notion.
Okay, thank you. First, my apologies for being late to the first lecture. Somehow I misread the schedule, but never happen again. Okay, so this is the joint work of Ivana Steiner Papuga and me, and also a group of authors from our universities, especially a professor who is, I should say, one of maybe the best statisticians at the University of Novi Sad, Professor Zagorka Lozano-Crvenković, actually a good friend of Ivana. So they discussed how to incorporate, to reconcile the unreconcilable, the statistical notions and fuzzy notions, basically. And the idea came, and thankfully to our provincial secretariat of Vojvodina, a small project was obtained, and through that project we will also present some results here. Actually, results here are part of the cooperation on that project. So we've actually done some overview how it's done, statistics and fuzzy logic combined. So we divided it into three parts. First is fuzzy to crisp, meaning implying some fuzzy methods to crisp data in order to obtain, especially, we will see some expectations of random variables and variance also, and what will be the problems in that way. Further on, we have the switch results. So if we have fuzzy data, which is, we can agree that every data can be or is fuzzier. So we try to apply some crisp methods to it, and we see what is there. So it was interesting, some results in testing hypotheses and the limitations and what do we get. And finally, fuzzy to fuzzy, which is the most interesting, obtaining using fuzzy tools on fuzzy data. So we see the next level of the double fuzziness, yeah, how it turns out. So this is maybe just a short overview. So we see how it's done. So actually, we start from a normalized fuzzy measure space, and we have a non-negative measurable, a real valued function. So the monotone expectation of f, denoted with obviously expectation concerned to the fuzzy measure mu, actually is, surprise, surprise, the Choquet integral of that function. So obviously we've seen a couple of times Choquet integral. This is a rather, shall I say, idea from the end of the last century. So the Campos and Bolanos have done this in 1989. Also, which is more interesting, they also try to introduce variance into the notion of variance, but there was a problem of comonotonicity. So the function f and the variance are not comonotones. So this sometimes yields a problem. So you cannot define variance with this. Okay, so also this probably, we had some statistician here, he would not be very happy, but here you can describe probability function via putting a fuzzy measure as a base of that probability function. This is a obviously well-known formula, and we are actually left that the probability of an element xn is actually the fuzzy measure of that element. Obviously, we have additivity and all the nice properties we have in classical probability if we defined this by a fuzzy measure. So this was done by Morales and Salmero in 2020, and variance can be calculated based on this probability measures. What is also interesting here, if we have crisp data, we can make a hypothesis that actually has a fuzzy premise. So we see here one fuzzy hypothesis. When we say the value of the parameter ni is a, where a is actually a fuzzy subset. Usually we're talking about fuzzy numbers, yeah. Here of omega. This is very interesting because what does not happen in the crisp case most often can happen here, that hypotheses can be in the same way accepted and not accepted. There is a degree of acceptance. So this is what problems we have when we fuzzify the premise of the hypothesis. Now we go to maybe some other case. So assume we have fuzzy data. So A is actually a fuzzy set, and we define expectations of the fuzzy set A as an integral, using an integral like this. Obviously, alpha is well known. So these are actually alpha cuts, and we assume that UA alpha is a uniform probability distribution. So actually, this basically means that A is a fuzzy number or a fuzzy quantity. How would you like it? What is the motivation for this is actually to compare two fuzzy numbers based on their expectations. And we obtain here basically some sort of a horizontal ordering. We will talk about orderings later. So I will tell you later what is the idea with these orderings. If we wanted to put some weights on the alpha cuts, or give, for example, stronger weights on alpha cuts with larger alpha, we can insert this function f, the weighting function, and we obviously obtain a bit more profound ordering on these sets. Now, this maybe bit more interesting. So what is a fuzzy random variable? Is actually a fuzzy number valued function from a sample space omega. What does this mean? This means that a fuzzy random variable is X is a fuzzy random variable if its alpha cuts or border alpha cuts are also regular random variables. So this is the way to define a fuzzy random variable. Very nice, very elegant way through alpha cuts. And obviously expectation is then somehow natural to calculate. So expectation of X is actually a fuzzy set where the limits of alpha cuts are actually expectations of the random variables that are alpha cuts of the fuzzy random variable. So this is very legit. Now we can have a hypothesis testing based on this. So if we have a fuzzy random sample, meaning large x tilde 1 to x tilde n are independent fuzzy random variables with a normal distribution, then if we take samples of this data, we obtain random numbers, and we can test the problem whether the expected value will be some fixed fuzzy number mu 0, and we do it based on the alpha cut. So we take the maximum alpha that satisfies this, and we get a degree of acceptance, or on the other hand, we get a degree of non-acceptance if we have a strictly larger value. So this is an interesting way to test fuzzy hypothesis with some sort of a crisp type testing. Also, this is one interesting way to find the expectation, but this is more of a vertical type of expectation. This expectation is based on a fuzzy measure. So actually, expected value of an empty set is 0, of a full set is 1, and all other fuzzy sets are in between. So this is some sort of a, I don't know, strength of a fuzzy set I can describe, not the expectations as we are used to from classical statistics. You know the names, Clement and Messier, that made this. And they actually have 3 types of expectations, which they gave in the axiomatic form. And also they characterized each of these expectations. You recognize, obviously, Choquet, Sugeno, and Shilkret. And there is a characterization of these expectations, meaning if A is comonocton additive, then it must be a Choquet. If it's comonocton maxitive and minim homogeneous, it must be a Sugeno. And finally, Shilkret if it's comonocton maxitive and positively homogeneous. Now, we have a result by Ivana and the professors, 2 professors from our group, Gabriela Gruic and Zagorka Lozanov-Cvenkovic, which they characterized, they combined the previous approach with the approach 2 slides ago. So they basically used the general fuzzy integral to find an expectation. And this is an obviously interesting generalizing result. Finally, we can also do some hypothesis testing. In a sense, if we have fuzzy data, so imagine we have fuzzy expected value and fuzzy variance or fuzzy dispersion of a data. So how do we test that data? We actually introduce vertical ordering. This is from the old days, I should mention. Ulrich Bodenhofer, we all know him, historical participant of this conference. Basically, if you rank fuzzy numbers based on the vertical position on the real line, meaning 5, the number representing 5 plus minus 1 is lower than the number representing 7. So we see this first upper left picture. Obviously, the blue number B is larger than the red number A. What becomes interesting, what is actually new and proposed by myself. So we introduce when numbers are comparable, like it's the first uppercase, it's okay. But what when we have something like this, and this second is obviously interesting because when you look at the form of vertical ordering, obviously B is a fuzzy subset of A, but vertically you really cannot decide because the left part of A is more to the left than B, but the right part of B is more to the, so it's somehow, it's a tie score, you know, like maybe in football today, you know, we have to divert to penalties. So the score is 0.5. And also we have these two overlappings when here, for example, the right part of A is larger than the right part of B, but there is a problem that we see that 1/6. So basically this is when they quarrel. So we can agree that just in that small part, B is larger than A, which is actually 1/12. Why 1/12? Because you multiply here by 0.5, you know, because left and right side you compare. And this is a complete mess. They interact too much. So you obtain this sort of a degree. You can look at the slides later if you want to calculate more precisely. I don't want to take your time. So basically, what do we use these results for? If you want to test the hypothesis whether mu is equal to mu nulla, if we suppose that dispersion is also a fuzzy number, we use regular fuzzy arithmetics, you know, addition of fuzzy numbers, multiplying by constants. So we take a sample of fuzzy numbers. We take its arithmetical mean, you know, we add them up and divide them by 1 over sample, and we subtract these two fuzzy numbers. And actually, acceptance degree of a hypothesis is this F relation. So if our difference falls within, you know, the good part of the distribution, then it's okay. If it's on the other side, then it's not accepted. But if they overlap, so if this also, we multiply the dispersion, you see we also have this set value from the quantile. If you remember the classical formula, this is the generalization of the classical formula. So basically, if they overlap, then we use this formula to obtain how much they overlap. And this is what we obtain here. So basically, Mirko said I have 5 minutes more, but I was looking at 2:20. But okay. Okay, so obviously we are open for more ideas. This is just ongoing work. So some papers hopefully to be published, one chapter. So thanks for your attention. And
Thank you for your talk. Thank you for helping us to get into back to the schedule, but we can have some questions. Are there any? If not, I'm happy that the next talk will start just at the right time.
thank you.
And the third and last talk of this session will be presented by Emil Skalugins. It's a joint work with Alexander Shostak, and it's about functors in fuzzy category theory.
Thank you for introducing me. My goal today is to reignite an interest in the field we would like to call fuzzy category theory. My co-author has done great work in explaining the differences between fuzzy categories and categories of fuzzy structures. Also was providing examples where classical category theory falls short. I'm now taking on the next step and trying to expand this theory. So before we go in straight into the definitions, a brief summary of what a fuzzy category is. Fuzzy category theory describes category-like structures in which objects and morphisms have assigned a membership degree. And this allows us to relax the requirements on objects and morphisms so that we can obtain models for situations that cannot be directly described using the tools of classical category theory. In another sense, the membership degree of morphisms and objects also provides local context in an otherwise context-free environment. So if you're working with a fuzzy structure, we also have to introduce a lattice. For now, it is defined as a GL monoid, but you can think of it as any strong enough residuated lattice. Every real-world example would use an NV algebra anyways. Now, a fuzzy category is a traditional category that has been enriched with two additional functions that measure the membership degree of objects and morphisms. And also they satisfy a few more conditions. The first two have to do with the bounds of the membership degree of morphisms, and the third one just states that the membership degree of an object should coincide with the membership degree of the identity morphism. Now, about embedding crisp categories, it's quite easy to see how we could embed crisp categories as a fuzzy category, we just define the membership degree as maximal. In a way, this a simple corollary of this is that every theorem that is true in classical category theory will also be true in fuzzy category theory, but we want to modify this theory just so that the membership degree gets respected. So we might modify our data, but classical category theory might not respect the membership degree. So we can also go backwards. If we take alpha cuts of our object class and morphism class, we get sets or classes of what we call alpha objects and alpha morphisms. And if this level or cut is taken at an idempotent element so that composition is conserved, we can obtain what we call threshold categories. And there's two special cases. When we take the threshold at the top element, we get the top frame, and then at the bottom element, we get the bottom frame. The top frame category is the most restrictive category in this sense. Now, for some examples. For instance, we can easily describe a membership degree for L sets. If we look at the crisp category of L sets, we just assign the membership degree as the infimum of its fuzzy subset. So whenever we're interested in only the object degree, we can assign the membership degree of morphisms to just coincide, not coincide, but to be expressed in a way that is synced with the membership degrees of the starting and finishing objects of the morphisms. And also, one thing you should know that the top frame category is the crisp category of sets, but the bottom frame is the crisp category of L sets. And we can use this framework to actually describe almost any crisp category which has a structure that has an underlying L set support set. So for instance, if we take the L groups in the Rosenfeld sense, we can assign a membership degree to each of the groups by just looking at the supporting L set. And in a similar vein, we can obtain both the crisp classical group category and the crisp L group category. But by estimating these degrees of potential objects in fuzzy categories, in a way, we narrow down the object class from the original crisp category. Instead, we could widen the class of objects by dropping some axioms, for instance, imposed on L groups. So instead, we could look at all pairs of groups and its fuzzy subset or L subset without checking the validity of the L group axioms. And now we could measure the degree to which such a group is an L group using our implication. So we test both axioms and test how well these groups satisfy the axioms in a simple, lazy manner. When we don't care about morphisms, we just sync them with the objects. And in this case, the top frame is the category of L groups instead of crisp groups. But we cannot only focus on objects, we can also focus on morphisms. If we return to the example of L sets, we can expand the class of morphisms to include every morphism between the underlying crisp sets. So we take the morphisms from the category of sets. This time we can measure the degree a morphism is a real morphism between L sets by a similar structure. And this time we just take all objects to be real objects by setting the membership degree to be maximal. But in a way, functors already play a role in all of these examples, because whenever we borrow a larger class of objects or morphisms from another category, we have to make sure that they play nicely together. And this is usually accomplished with functors. This is just like a general framework. Now, those were crisp functors. Now we would like to look at functors inside fuzzy categories. The problem with classical functors are that they might not respect the membership degree. So delta functors between two fuzzy categories would be a classical category, but additionally, it would respect the membership degree up to delta. Well, one thing you should notice is that since we can keep continuing this inequality to the left, every delta functor is also a zero functor. The keen eye of you would have noticed that the condition was on morphisms and not objects, but if we remember that object degrees are synced with the identity morphisms, then an extra property is satisfied. And then additionally, if we have a strong enough lattice, for this instance, a Hating algebra, and also if the membership degrees of morphisms and objects are synced, morphism and object membership degrees are interchangeable. So how do these functors behave? There are some nice properties. One of them is that if we look at delta functors and delta is an independent element, then we can restrict this functor to the threshold categories, and we will receive a crisp functor between the corresponding crisp categories. So in a way, a delta functor brings a class of crisp functors for each lambda less than delta. And as I mentioned, each delta functor is also a zero functor, and it identifies all of the crisp functors, because we can only assume a crisp functor is at best a zero functor. That was the groundwork put in by my co-author. Now my job was to push this forward to adjoint functors, and to get to adjoint functors, we will need to look at functor composition. And the thing about functor composition is that we could have two zero functors, but their composition be maximal functors. That sounds like a great deal, but we would like to look at it in the opposite direction. If we know that two of these compositions are one functors, we cannot infer any information about the components. And it gets even worse because we can construct examples where there are no degrees of freedom. As in, we can know the three of the functors are non-zero, but the fourth one still will be a zero functor. So there needs to be an extra condition, such as extra conditions on these functors, so that we can tell that the resulting functor respects membership degrees. And one of these conditions was the y. Was we just we ask that the functor g is non-increasing with respect to f, and then a non-increasing part is with respect to membership degrees of morphisms. And with such an extra condition on functors, examples like the previous one do not exist. Now, to get to adjoint functors, we have to make a pit stop at natural transformations. Since natural transformations are just morphisms between functors in the functor category, it should come to no surprise that the condition we additionally ask on natural transformations is quite similar to the one that was with functors. So we ask that each component of the natural transformation respects the membership degree up to lambda in this case. And we have natural transformations. We can define what we mean by alpha adjoint functors. So two functors form an alpha adjoint functor pair if there exist alpha natural transformations, which we know as the unit and co-unit. Now, a big question about adjoint functors is when can we expect the existence of this pair? And in classical category theory, there's well-known theorems, the adjoint functor theorem, that gives a sufficient and necessary condition, such a functor admits a left adjoint. Unfortunately, we need to respect the membership degree, so this is only currently a sufficient condition. The good thing about these objects in comma categories, which I will not delve into, is that these conditions are automatically satisfied in crisp categories. So by giving this extra condition, we can give a sufficient condition such that a delta functor admits a left adjoint up to a level delta. And then another important result in my eyes that was obtained is the obtaining of crisp adjoint functors from delta adjoint functors. So whenever we have a delta adjoint functor pair between categories and delta is an idempotent element, we can get a class of adjoint functors in the crisp threshold categories between the respective functors. So one of the easiest examples is if we take the crisp categories of set and group, then we know that there's a classical adjoint functor pair which respectively corresponds to the free and forgetful functor, but we could also find analogs in the fuzzy set, fuzzy categories. And if we can find an adjoint functor pair in the fuzzy categories, we would actually obtain a class of adjoint functors in all of the crisp categories. So whenever we take at a certain threshold, we will get the adjoint functor pairs in the categories between L sets and L groups, or between the categories set and group. So from a single fuzzy adjoint functor pair, we can extract multiple well-known crisp adjoint functor pairs. Now, that was the extent of my research, was to get that far. In summary, using fuzzy categories, it is possible to model situations which we cannot directly describe using the tools of classical category theory. And also, fuzzy categories can provide local context to objects and morphisms. In addition, fuzzy adjoint functor pairs can be used to obtain whole classes of crisp adjoint functor pairs. This is the extent of the theory. As I said, the resurgence has been only recent. So if I want to talk about the next steps, we'd like, at least in my PhD research, to maybe try to get to representation theorems. That's when adjoint functors and functors play a big role. Oh, thank you for your attention.
Thank you. Thank you also for making my role easy. And we really have time for discussion. It seems that people are tired, no surprise. They have apology. And for those interested, I just want to remind you that this session is over, but the session B has one more talk, so that which starts now, so you can still learn something. Thank you for your attention.